Thank you, Obli, for that nice introduction. You are a good friend, I can say that. Let me acknowledge my Professor Jun Zhang from the University of Hawaii, and I'll be relating some of the work done jointly with her. So let's look, I'm a signal processing, I'm a person that likes data, looks at data. And of course, we are all very aware that the data is very sobering. And the numbers are absolutely astounding. If you go here and go back about a year or so ago, the numbers were so small that maybe the people might think, oh, this how can this become a problem? And nowadays, today, 11 months or so, the numbers of new cases are reaching the 110 million mark, and in the US alone, 28 million. And the number of deaths is a very sobering number, reaching the 2.5 million worldwide, and the US, unfortunately, close to the 500,000. So the issue is what can and what should we be doing to prevent or to be better aware in the future? And from my perspective, I look at things driven by data. I look at things that evolve with time. And so epidemic dynamics is clearly one of the big problems. But epidemic dynamics by itself is a very complex and a complex phenomenon. And so the question is how much engineering, how much of the techniques that we usually use can be useful in dealing with the phenomena like that. And clearly, that's an issue that also depends on the stage of the epidemics that we are in. If we are at surveillance, if we are at before even the outbreak occurs, then clearly we are trying to predict and prevent the onsetting of the disease, and that should be done with different approaches. But if we have already identified somewhere in the world, like in Wuhan, some cases, or in the US early on in Seattle, then clearly we are at a different stage, and maybe what we should be doing, the tools that we use to analyze these things might be different. And finally, when the disease itself is full-blown into an epidemics, then clearly we need different ways of understanding the phenomena. And these different stages are related to plots like this that reflect that dynamics with respect to certain statistics of the disease. So what do I mean by pandemics and engineering? What I mean is that we technologists tend to abstract the reality and come up with simplistic approaches to that reality that we call models. These models usually couple the methods that we develop to analyze with some understanding of the fundamental principles behind the phenomena that we wanted to study. But we don't do just that. We also combine that with data. And so let me rearrange this just for so that doesn't show too much. So this is what technologists like me like to do, is to work with the people that understand the fundamental principles, and those are the domain experts. And so in this endeavor of trying to use engineering approaches, the algorithmic approaches, learning approaches to these problems like COVID, we cannot sit in our ivory tower, come up with an understanding. We have to work, we have to be open, we have to work with the people that really understand what's behind the phenomena we are trying to understand. And so it's clearly a highly interdisciplinary approach that we need to take. So, and when we talk about zoonotic and emerging pathogens, then the problems are even more complex, because now you have, according to Wolf and Alter and Lloyd Smith and others, in papers they wrote in 2007, 2009, these zoonotic dynamics actually go through phases, and you move from an animal population to a human population through stages where animal and the population, so they interact, and we need to then have in mind as we go through these stages how these complex systems interact among themselves. So the models need to account for the coupling between these different stages. And the models, of course, if they are going to be useful, they need to be accurate. And as I said, engineers, signal processing, machine learning people, we don't work just with the abstraction of the model. We work with the model, but we also look at the data as it's being collected in real time to adjust the models or to make better predictions or to design better actions. So if you look at models, the models that are dominant in much of the analysis is what we call the dominant epidemic models are compartmental models, are models that assume that the population, so they look at a single population and they assume that the population is divided in compartments, susceptible, infectious, and so forth, assume homogeneous models, deterministic, or at least they look at the asymptotics of very large populations. They come up with some differential equation type models that the behaviors are very simplistic, exponentials till they reach subsaturation, and usually they are parameterized by very few parameters, like the effective reproductive number that all of us have been bombarded in the last year or so. So if we want to be more accurate, we have to go beyond that. And I want to call attention to, okay, we are not going to drop this nomenclature of compartmental models, but they have to reflect many of the stages through which individuals go evolve. And so it's not just an SIR or SIS, it has to also expose the different infections individuals that are asymptomatic or not, and so forth. So they have to be more complex that way. But they have to take into account that people move and people interact with others, but they don't interact like traditionally one assumes in these deterministic homogeneous models where anyone interacts with anyone else. They interact through either their mobility flows in the initial phases through their long distance travel, or when we are at the outbreak or epidemics through their networks of contacts. So these networks have to be taken into account if we want to have realistic models. And of course, everything is random. And so there has to be statistical random interactions among these agents of the population through their networks of contact. And what that means is that now we have networks, we have randomness, we have highly complex systems. In some work that I did with Professor Zhang, we made simplistic assumptions on some other parameters, like, for example, every agent infects with the same probability or same chance any other agent through their network of contacts. So this is homogeneous parameters and so forth. And we came up with, under some assumptions, some simplicity, we came up with what would be the probability that once you look at this population with their networks of contact, particular individuals becoming infected while others don't become, with a certain probability. And it has several statistics there. Here is where the network of contact intervenes. I'm not going to go into the details here. What's important also is that just like with the simplistic models, the parameters themselves define regions, and certain regions of the parameters where maybe healing dominates versus contact infection first contact infection or vice versa, you end up with different expected, most likely distribution of infected people or not. So tracking the values of these parameters is extremely important. And here are examples where, depending on the parameters, depending on the network, you might come up with the most at-risk population, for example, being this. But if you change the parameters, still the same network of contacts, then the risk of population enlarges tremendously. And here is another example with a different network, different parameters, and you see that here the network structure of contacts, the network of contacts tells you that this part here is the more at risk. But if you change the parameters, then you get something else. So the more realistic models, then we have to go back and make these more realistic by capturing heterogeneities. So agents, individuals will infect others with different chances. Some individuals, super spreader events happen. So some individuals really are very prone to infect others, while others are not as prone. So that has to be taken care of. And there is some nice work done by Lloyd Smith back in 2005, if I'm not mistaken, on that. Then there are new strains that come along, so give a temporal heterogeneity. And as I mentioned, when we talk about zoonotic, then we have coupled networks, themselves heterogeneous. All this complexity needs to be taken care of. And so I think that what we need is to start to enrich many of the models that exist, many of the test beds, so that we can explore what-if scenarios, and in particular get forecasting, get the impact of different control policies, where and who to vaccinate, couple the social and economic costs, and collect reliable data so that we estimate the parameters. We know what we are talking about. The models reflect the real world as it's evolving, rather than us coming up with the numbers that do not, with the parameters that do not correspond. And if we are talking about the monitoring before the pandemics, we have to develop schemes that can monitor. And this is my last slide, and it's just to say that test beds, of course, the data is key to estimate, as I mentioned, the parameters, but it's key to validate our models. And one big question that came from the sessions this morning and came from some of the outbreak sessions that I participated clearly is, how do we monitor before the things really happen? How are we aware that things might around the corner arise, and before they become outbreaks and they go into pandemics? And for example, with respect to the COVID, is it bat population? But it's not just that animal reservoir, is also the intermediaries, maybe domestic animals or maybe others that are the ones with whom the humans more interact with and are more prone to get infected. So this is a very complex problem. I think there is a great opportunity, great interest, great challenges. It's very interesting, and I think what we need is interdisciplinarity here and work with our colleagues from different areas and different fields. Thank you.